Hello everyone, welcome back. So today we are going to take up some more mechanics problems. So the first question, so this is the first problem and this is from circular motion you could say. So we have a bead that is connected with a fixed disc of radius r and it is connected by an inextensible massless string in a smooth horizontal plane. Okay, so the motion is happening in the horizontal plane, gravity is into the plane. Okay, if the bead is pushed with the velocity of v naught perpendicular to the string, the bead moves in a curve and consequently collapses on the disc. So basically as the bead continues its motion, the length of the string will keep reducing and after a while it'll collapse on the disc. And we have to talk about the initial angular acceleration. Okay, so what they're asking is, okay, so let's say after some time the particle is over here, right? So if I draw a tangent, we can see that the string has swept out some angle theta. So they're asking the double rate of change of that angle theta. Okay, so that's the angular acceleration that they're talking about. And we also have to comment on the distance traveled by the particle. Okay, so pause the video and give this problem a try, guys. Then check out the solution. Okay, guys. So this is the sketch of the initial situation and the situation after some time. So there are some important points here. So the first idea is that the string is inextensible. Okay, so and because of this, there is a very important realization. Okay, so and that is when the string actually reaches this point, let's say this particular point over here is some point P. And let's say the initial point was O. So when OP length of the string is on the cylinder, the string is now a tangent to this point P on the cylinder. So here the important idea is that the velocity of the string at this particular point is 0. Now, why is the velocity of point P 0? It's because if you observe this length OP, it's actually fixed, right? This point O is fixed, which means P cannot move along the cylinder. So now the point P is instantaneously at rest. So, and the entire string and the mass M, we can say it is performing a circular motion about this point P. Okay, so basically this point P can be treated as an axis about which this string and this mass is performing rotational motion. Now let's mark down some angles. So let's say the angle subtended by these two lines is theta. Then the angle between the tangents will also be theta, right? The first tangent was horizontal, so which means even this angle is going to be theta. Okay, now the second idea is that the tension force is actually perpendicular to V naught. So if you observe the particle was, so it was given that the particle was projected perpendicular to the string. Now as the tension T is perpendicular to V naught, and if you observe it is perpendicular to the velocity vector at all times. So what that actually means is the velocity V naught has a constant magnitude throughout the motion because there is no force in the tangential direction that can change its speed. If there was friction present, then V naught would have changed its magnitude, but here T and V are perpendicular. So in short, you can say T dot V is actually 0, meaning tension cannot deliver any power or basically do any work to change the velocity. So basically V naught is going to remain a constant. Now we know this point P acts like an instantaneous axis for the string and mass system, right? So we can write down d theta by dt, which is basically the omega of the line, as V naught divided by, so let's say the length of the moving part of the string is L. So this will be V naught divided by L. Okay, and let's take the initial length of the string to be L naught. Okay, so now the moving part of the string, that length, if it is L, this length OP is going to be, we can figure out using the arc length formula. That is just going to be R times theta, right? So L is going to be L naught and R theta subtracted from it. So this is going to be V naught divided by L naught minus R theta. So now basically we have the omega of the line as a function of theta. Okay, so the angular acceleration, we can just write it as omega d omega over d theta, right? So I'm going to substitute omega that we figured above and the derivative of omega with respect to theta. Okay, and we'll get this as for the expression of alpha versus theta. Now at t equal to 0, the string was horizontal, which means theta is 0. So if you put theta equal to 0, we'll get the initial angular acceleration as V naught square R upon L naught. Okay, and that would be option B. So now we will talk about the distance traveled by the particle till it collides with the disk. So for that, we'll talk about the angular velocity expression once again. So here, if you observe, we have a variable separable differential equation. So if I So if I bring the like variables on one side, it'll be L naught minus R theta times d theta equals V naught dt. Okay, and now we can set up some limits. So at time t equals 0, theta limit was 0, and we need the time when the particle collides with the cylinder, right? Okay, and we need the theta limit for that. Okay, so what that implies is, so basically when the particle hits the cylinder, what is the total angle that has been swept? Okay, so we know that the total length of the string that would be wound around the cylinder is going to be L naught, right? So if I divide L naught by the radius of the cylinder, I'll get the angle subtended by that, the L naught length. I'll get the total angle covered by the string till the by the moment it collides. So for example, if you put L naught equals 2 pi r, right? Imagine for a second that this length was 2 pi r, then 2 pi r by r will give you 2 pi, which means the length, the bead will complete one revolution and it will come collide with the disk at point O. So you can take the example for any particular length, and so basically the theta limit will be L naught divided by r. Okay, so now if you observe, they asked us about the distance traveled, right, rather than the time of collision. Now guys, whenever distance is asked, right, and the speed of the particle is actually a constant, it doesn't really matter what the trajectory of the particle is, right? At each point, the velocity, if the speed is actually a constant, then if you take any small segment along the path whose length is, let's say, ds, then we can always write ds as the speed v naught times the small time dt, right? So if you integrate, now what is distance? Distance is just the magnitude of all these ds elements added up, right? So basically it is integral of ds. So with this we'll get the total distance traveled as just v naught times the total time, right? So distance is pretty simple. It does not matter what the curve actually is. As long as the speed is constant, it is speed into time. So if you observe on the right hand side, it's just that particular integral, right? It's speed into time. So the LHS is the distance that we're looking for. So if I integrate this expression, you'll get the answer as L naught square by 2r equals v naught into t, which is the distance, right? So the answer will be B and C for this question. Now let's move on to the next one. Okay, so in this question, we have a rigid massless rod whose length is L, and it joins two particles each of mass m. So the rod lies on a frictionless table. Once again, gravity is not in picture. A particle moving with speed v naught collide directly and elastically with one of the particle as shown in the figure. So the collision is given to be elastic in between these two masses and they collide head on, right? We have to talk about all these particular options which are kind of interrelated, right? So let's draw a diagram and discuss what's really happening. Okay, so this is the diagram of the situation. So this particle will collide head on with this particle and we have a rigid massless rod. Okay, so the tension in each cross section is going to be the same. This mass over here is approaching with a speed of v naught and all of them have the same mass. Okay, so when particle 1 collides with particle 2, so it will exert some impulse on this particle over here, right? So let's name this impulse as J1. Now, while this mass over here is being accelerated by their interaction force, obviously tension will start developing in the rod as well, right? So basically the tension, so that tensile force will accelerate the third mass as well, right? Okay, so that is kind of roughly what is happening. So basically if we want to draw the after picture of the situation, now there is like two ways to draw the after picture. So first is like assume some first particle finally has a speed of v1, okay, and since the rod plus the two mass system is basically a rigid body, we can say that it'll finally gain an angular velocity of omega and the center of mass starts translating with some velocity v2. So this is one way of writing the final situation, but I'm just going to take both of their velocities individually. Okay, so I know the tension here applied by the rod on the third particle is along the rod. So what that means is this guy will have the velocity along the rod. Okay, so and I'm going to call this as v2. Okay, now by rigid body constraint, we know that if this end of the rod is moving away with v2, then this end should also move along the rod with the same speed of v2, right? And this is by the constraint that otherwise the rod's length will change, right? Okay, now if you observe the second particle, this guy's velocity is incomplete because this guy gets an impulse along the rod, but he also gets an impulse perpendicular to the rod, right? Because if you observe the first impulse J1 and J2, they might have some component in the perpendicular direction. So we'll have to consider a component, let's say V3, perpendicular to the rod as well. Okay, so this is the velocity diagram in the final situation. So we don't really have to care about the center of mass because we individually know the velocity of the masses. So firstly we'll write the equation for the coefficient of restitution, right? So the approach velocity between these two masses was V0, and the separation velocity, if you observe, so this angle was given to be 45 degrees, right? Separation velocity will be V2 plus V3 cos 45 and minus V1. Okay, so this would be our first equation. And secondly, let's just conserve the momentum. Okay, so secondly, we'll just say that the net momentum in the vertical direction is conserved. And so now we'll just conserve momentum in the x and y direction. So first, if we conserve it in the y direction, initially the momentum was 0. Finally, this guy has a component of mv2 cos 45 or sin 45. It's the same thing. So it's going to be mv2 by root 2. And this guy has a momentum of mv2 by root 2 minus v3 by root 2, right? So the m's cancel out and we get v3 equals twice of v2. This would be our second equation. And our third equation would be the momentum conservation in the x direction. So initial momentum was mv0 in the x direction. Finally, it is mv1. Due to particle 3, it is mv2 by root 2. And due to particle 2, it's going to be m times m by root 2 times v2 plus v3. And v3, I'm going to just write it as 2v2. Okay, so this would be our equation number 3. So now all we have to do is solve the system of 3 equations. So after solving all the 3 equations, we get these 3 values for v1, v2 and v3. So if you observe the first particle, it rebounds with a velocity of v0 by 7, and that was actually in one of the options. And now we have to talk about the so now they're also asking us about the magnitude of impulse on the rod by the rod on this particle B. So basically we have to find the impulse on this particle by the rod. Okay, so the tensile force, so basically they're asking us about integral of t dt, right? Which is actually the same even for particle C, right? Even the impulse of tension, as this is a light rod, the tension force is going to be identical. The tension force acting on B and C is going to be identical, right? So the impulse of tension on particle 2 is the same as the impulse of tension on particle 3. So, and on particle 3, if you observe, initially it was at rest and finally it gains a velocity of v2. So we can say that the impulse of tension on the third particle is just going to be the change in linear momentum of the third particle, which is m times v2. This is going to be 2 root 2 mv0 by 7. So option D would also be correct. Now we have to find the angular speed of the rod and VCM after collision. Okay, so now if we observe this diagram over here, if we observe with respect to this particle 3, the good thing about this is that it does not have a perpendicular component to the rod, right? Its velocity is along the rod. So now if we observe particle 2 sitting here at particle 3, we'll only observe a component v3, right? And distance of the particle from us is going to be L, right? So if I define this angle as some theta, so then I can say d theta by dt, which is also the angular velocity of the rod, is going to be v3 divided by the length of the rod L. So this is going to be 4 root 2 v0 divided by 7L. Okay, so option A is also correct. Now, so now we only have one more question left, which is the velocity of the center of mass. So once again, we can use our frame of our observer here at point 3. So with respect to our observer here at point 3, all points on the rod will move in circles, right? Okay, basically this point over here can be treated like a hinge, which means the velocity of the center of mass is going to be L by 2 times the angular velocity omega of the rod. So if we calculate this real quick, it'll be 2 root 2 by 7 v0. So, but this was with respect to our observer 3, right? So in the ground frame, we'll have to add the velocity of the observer 3. So basically, if we want to write it in equations, then velocity of the center of mass relative to particle 3 is actually L omega by 2. And let's call the perpendicular direction as y cap. So this is going to be y cap, okay? And I'm going to call the direction along the rod as x cap. So velocity of the particle 3 is actually v2 in the x cap direction. So now all we have to do is add this vectorially. So diagrammatically speaking, the relative speed is L omega by 2 in this direction, and we'll have to add the velocity of 3, which is v2, vectorially. So equation wise speaking, all we have to do is add these two equations. So we'll get the velocity of the center of mass in the ground frame. So this is going to be v2 x cap plus L omega by 2 y cap. And so now x cap and y cap are mutually perpendicular. So the speed of the velocity of center of mass is going to be 4v0 divided by 7. Okay, so even B option is correct. So all the options are actually correct in this question. So now let's move to the last question. Okay, so this is the last problem. Here we have a block whose mass is capital M, and its height is given to be 2b and breadth is b, and the plank that it is kept on is actually rough, and it has the same mass of capital M. Then we have a light inextensible string that is connected to the upper end of a block and pass through a light and smooth pulley. So the coefficient of friction is actually given to be 0.3. So first we have to talk about the max value of the mass of this block A, so that the block B neither topples or slides. So we don't want the block to actually topple, or we don't want it to slide relative to the plank. Okay, so that's question 1. So let's try to actually solve for that. Okay, so this is the diagram, and the unknown mass, I'm going to call it as small m. Okay, so whenever we have a toppling versus slipping question, so firstly we'll take the assumption that only one of the phenomena happens. So first we'll assume that the block does not topple. So first we'll work with this assumption. Keeping this assumption in mind, we'll solve for the value of m at which slipping will start. Okay, so till the point of slipping actually starts, we know these two masses will move as a system. So they will have some common acceleration. Let's just call it as a. So which will be the same acceleration with which the mass m actually descends because of the inextensibility property of the string. Okay, so now we can write 1 F equal to ma equation to determine this A. So if I take all the three masses as a system, forces along the direction of the acceleration is going to be m into g, right? There is no force in the horizontal plane. There is no friction from the ground. The other friction forces are internal, so we don't have to consider that. Tensions are also internal. So the force along the direction of acceleration is just mg, and this would be equal to the total mass, which is 2 capital M plus small m times the acceleration a. So from here, a turns out to be this value. Okay, so now let's separate out the block. So it has a force of tension acting on, and the friction from the surface will be in the backward direction, and on the block it will be in the forward direction. So it's better to take the FBD of this plank on the ground. So we can say F equals capital M times A. So if I substitute the value of A over here, we'll get this expression. So we want the friction between the block and the plank to not exceed its maximum value, which is mu times the normal reaction, and the normal reaction is just equal to the mass, just equal to the weight of the block, right? So we want it to not exceed mu capital Mg. Okay, so after doing a little bit of algebra, we'll get m should be less than or equal to 24 divided by 7 kg, which is around 3.4 kg, right? So basically, if you assume that toppling never happens, then the slipping starts happening at small m equals 24 divided by 7 kgs. Okay, so now let's work with the second assumption that the block does not slip, and now let's try to find out the condition for toppling. Okay, so once again, the block is accelerating with some acceleration of a, and same with the plank, right? But for this purpose, we don't really care about the FBD of the plank, right? So let's name this edge point as P. So we know as it gets closer and closer to the toppling event, the normal reaction actually shifts closer towards the edge P, right? And while it is just about to topple about this edge P, the normal reaction will actually just coincide with the point P, and obviously friction will also be passing through this particular point. Till the event of toppling actually starts, the block will be in rotational equilibrium. Why? Because it doesn't have any angular acceleration, right? So we can say the alpha of the block is actually 0. So now all we have to do is balance all the torques about this particular point P. Which all forces do we have to consider? So we'll have to consider this tension T and then the weight of the block. Okay. So which, let's just mark it as mg. And the torque of N and torque of F have line of actions passing through the point P, so they won't have any torque about the point P. So these are the real torques, but there is another key point here, and that is the point P is actually an accelerated point. Okay, so as we can see, the entire block is translating with an acceleration of a, right? So basically, the deal with accelerated points is that if you want to write the net torque expression about the point P, so I'll make a proof video on this in the future. But basically, if you want to write tau equals dl by dt about this particular point P, which is an accelerated point, right? About some random point which is accelerated, then you have to consider the pseudo torque due to the acceleration of P. So basically, the point P is being accelerated towards the right with the same acceleration A of the rigid body. So we'll have to consider the pseudo force due to this acceleration A, and the pseudo force will be minus ma on the center of mass, right? And we'll have to consider the pseudo torque due to this ma force about the point P. So basically, if you observe, mg and ma has a counterclockwise torque about the point P, and tension has a clockwise torque about the point P. So the torque due to all the real forces plus the torque due to the pseudo forces, this should add up to 0. Why? Because the block is in rotational equilibrium. So the real torques, so now we'll just do the clockwise torques equals anti-clockwise torques. So the line of action of ma is at a distance of a from the point P. So we'll say ma, distance of b from the point P. So mab is a torque due to ma, and due to mg, this distance is going to be b by 2. So it'll be mg into b by 2. And this should be equal to the tension force T times 2b, right? So T turns out to be ma by 2 plus mg divided by 4. So if the value of tension T exceeds this particular value, now the value of tension T we can figure out using the FBD of mass small m. So tension T is going to be m times g minus a, right? So now if we now let's try to solve for this equation. Okay, so basically after solving this expression and substituting the value of a from our earlier equation, we get that the value of m for which toppling actually starts is at 8 by 5 kg. So if you observe, 8 by 5 kg is 1.6 kg, which is actually less than the value at which we figured out slipping would start, right? So which means if we want neither toppling nor slipping to start, then the mass small m has to be less than 8 by 5 kg. Because if it is greater than 8 by 5, then actually it will topple, right? So option A is actually correct. Maximum value of the block small m, so that it neither topples or slips, is actually 8 by 5. Okay. Now the second and third option, if you observe, the mass of m is taken to be 1 kg, which is less than 1.6. So we know that the block will neither topple nor slip. So basically we have to plug everything in this equation, right? So if the value of m is 1 kg, then we can, for m equals 1 kg, we can find out the acceleration from this equation. So it's going to be 10 by 9 meters per second square. Now the force of friction is just capital M times A. So capital M is 4, right? So the force of friction in this case is going to be 40 by 9 newtons, which is what they asked in the second option. Now for the third option, they're saying, in this case, what is the line of action of normal? What is the distance between the line of action of normal and the center of block? So we discussed earlier that when toppling is about to start, the normal shifts to the edge, right? So for this particular value of m equals 1 kg, the normal would have shifted to some point over here, right? So they're asking what is this distance x from the center of mass of the block. Okay. So the only difference is that in this expression over here, right, the torque of T doesn't change. The only torque that changes is the torque of mg. Now it will be mg times x. Now it will be mg multiplied by x instead of mg multiplied by b by 2, right? So the equation changes to mab plus mgx equals t times 2b. Okay, ma was 10 by 9. So I'm going to divide throughout by b. So this will become 40x by b. And tension is small m times g minus a. So it is going to be 1 kg times 10 minus 10 by 9. This thing times 2. So this would be 80 by 9. We can cancel out the 40s. So from here, x by b turns out to be 3 by 9, which is 1 by 3. So basically we are getting x equals b over 3. So the normal shifts towards the right by a distance of b by 3 if m equals 1 kg. So that's what they're saying in option C as well. Now in option D, they're saying the impulse given by the force of gravity on the block is 0 in a non-zero given time interval. Okay, so basically if I take my block B, they're claiming that the force of gravity, it will have a 0 impulse in a given time interval. So this would actually be wrong because the impulse of mg is just basically the integral of force times the time dt, right? And we integrate it from and we integrate it for a time interval. Now this integral is obviously non-zero. Yes, yes, it is true that the block's momentum does not change in the y direction, but that's because there is normal that is also providing an impulse. So both of their impulses actually cancel out. But to say that the force of gravity has a 0 impulse would actually be wrong. Okay. So yeah, that was it for this question. So if you guys enjoyed the video, make sure to like, share and subscribe. And yeah, if you have any doubts, you can comment down below. And that's it. Thanks for watching.